Welcome to the opening session of Professor T. Thrivikraman Endowment Lecture. This lecture is jointly organized by Department of Mathematics, Cochin University of Science and Technology, and Center for Topology and Applications, Department of Mathematics, Rajagiri School of Engineering and Technology, which is one of the 3 autonomous engineering colleges in the state of Kerala. This is the second lecture in the series. The lecture is instituted to mark our love and respect to our Guru, Professor T. Thrivikraman. After having his graduation in Sri Keralavarma College, Thrissur, Professor Thrivikraman did his post-graduation in University College, Thiruvananthapuram, MPhil and PhD from the University of Madurai. Professor Thrivikraman started doing research under the supervision of Professor M. Rajagiri, and later on completed his doctoral thesis on studies on compactifications and other extensions under Dr. T. Soundararajan. Professor Thrivikraman started his teaching career at Mar Athanasius College, Kodamangalam, from where he was sent to Madurai for pursuing doctoral studies. Later, he joined the Department of Mathematics of Cochin University as a lecturer in 1977. After 4 decades of successful teaching, he retired from active service on May 31st, 2003 from the Cochin University of Science and Technology. Professor Thrivikraman is a guide and guru to generations of students. There is hardly any college in Kerala that has not received his direct or indirect help. Almost every college in Kerala is likely to have at least one of his students on its faculty. He has given shape to the syllabi and curriculum in universities across South India. Professor Thrivikraman's scholarship in mathematics is astounding in its range and depth. His deep interest in diverse areas has made him an authority on a wide range of topics like topology, fuzzy mathematics, fractal geometry, frame theory, digital topology, graph theory, etc. He has graded 32 students for PhD degree. His deep knowledge of Sanskrit has helped him to move towards the philosophical dimension in his articles and books. He is an exponent of the history of mathematics as well. The Department of Mathematics, Cochin University of Science and Technology, developed in many ways during his tenure as the head of the department. A gentleman to the core and the personification of integrity and hard work, he could coordinate the affairs in the department with ease and win administration and praise from all quarters. In his leadership, Department of Mathematics, Cochin University of Science and Technology has become a prestigious department for postgraduate studies and research. He was elected as the president of Indian Mathematical Society during 2004-2005. Currently, he is living at Nileshwaram, Kasaragod, which is the northernmost district of Kerala, with his wife, son, daughter-in-law, and grandchildren. We are very much pleased that he and his family members are with us today to attend this event. With due respect and great pleasure, I welcome TT Sir and his family members for this function. Today, the lecture will be delivered by Professor M. Murty, A.V. Douglas Distinguished University Professor and Queen's Research Chair, Department of Mathematics and Statistics, Queen's University, Canada. I thank him for accepting the invitation to deliver the talk. He is going to talk from Canada, where the time is around 7:45 today morning. I cordially welcome Professor Murty for this opening session. Welcome, sir. To offer felicitations, we have with us Professor P.S. Srijit, Principal of Rajagiri School of Engineering and Technology, Dr. Shashi Gopalan, Head Department of Mathematics, Cochin University of Science and Technology, Dr. A. Vijay Kumar, Professor Emeritus, Cochin University of Science and Technology. I welcome all of them to this opening session. I welcome the faculty members of Department of Mathematics, Rajagiri School of Engineering and Technology, faculty members of Department of Mathematics of Cochin University of Science and Technology, students of Professor Thrivikraman, former colleagues of Professor Thrivikraman, and all the participants who have shown interest to attend this lecture. I welcome you all. Thank you. Now, may I invite Professor P.S. Srijit, Principal, Rajagiri School of Engineering and Technology, to offer felicitation.
Respected Professor Thrivikraman, Professor Murty, Professor Vijay Kumar, Dr. Shashi Gopalan, Dr. Vinod, faculty members of Rajagiri School of Engineering and Technology, Cochin University of Science and Technology, and other participants. I am extremely happy to felicitate the function organized in connection with the Professor Thrivikraman Endowment Lecture, which is jointly organized by Department of Mathematics, Cochin University of Science and Technology, and Center for Topology and Applications, Department of Mathematics, Rajagiri School of Engineering and Technology. There is no need to introduce our great professor, Dr. Thrivikraman. He is an Indian mathematician, and his contribution, I understand that, is in topology, fuzzy mathematics, and history of mathematics. He has promoted the mathematical research culture in the state of Kerala, which is evident from the number of PhDs which he has produced, more than 32, as Dr. Vinod has told over here. He was also involved with, I understand that he was also involved with Kerala Shastra Sahitya Parishad for the popularization of science in our state. And he has been with Cochin. He retired from Cochin University in 2003, and I joined at Cochin University in 2001. We are only very few interactions with Professor Thrivikraman. And needless to say, he has got several recognitions. He was the fellow of National Academy of Mathematics of India and president of Indian Mathematical Society. And I understand that by going through his CV, I understand that he has written a book on poems also. That means he is a poet also. And I take this opportunity to congratulate Professor Thrivikraman and also to wish him a healthy life for the many more years to come. I also congratulate the organizers of this endowment lecture, namely Dr. Shashi Gopalan of Cochin University of Science and Technology and Professor Vinod of Rajagiri School of Engineering and Technology. I also welcome our today's eminent speaker, Professor Murty, who is attending this function from Canada. I also wish all success to this program, and also I welcome all the participants to this program. Thank you very much.
Thank you, sir. Now, may I welcome Professor Shashi Gopalan, Head Department of Mathematics, to offer felicitation.
Respected Professor Thrivikraman sir, respected Professor Murty, Department of Mathematics and Statistics, Queen's University, Canada, respected Professor Srijit sir, respected Professor Vinod Kumar and Vijay Kumar sir. It is very happiest moment for this endowment lecture conducting jointly with the Rajagiri College of Engineering and its Department of Mathematics. In this occasion, I extend my sincere thanks to Professor Murty for joining with us this evening, and also for the management of Rajagiri School of Mathematics, and especially for Vinod Kumar sir and Srijit sir for conducting this endowment lecture. And the topic is very relevant, and we know that graph theory methods are important to understand the architecture and development and evolution of brain network. So in this situation, it's a very relevant topic is selection, and we have got a very good speaker in this moment. I extend my special thanks to Murty sir for joining with us. and wish you all the very best and also for this session. Thank you very much.
Thank you. Now may I invite Dr. A. Vijaykumar, Professor Emeritus, Cochin University of Science and Technology, to offer felicitation.
Thank you, my dear friends, and very good morning to Professor Murty. This event is organized in honor of our Guru, Professor Thrivikraman, with whom I have a very long association since 1978, when I joined Cochin University for my master's program. Then he was my guide, research guide also, and then continuously monitoring and helping us to develop the mathematics culture. Whenever we think about Professor Thrivikraman, I cannot forget his beautiful classes, though 44 years ago. He used to talk about compactification, alpha line, and so on. And I repeat what I said last year. I have not seen or I have not heard anyone else talking about compactification and alpha line more beautifully than what Professor Thrivikraman used to do. He has given us the training to become a professional mathematician. His blessings has taken us a long way, not only myself, but plenty of students of mathematics in Kerala, and also the wonderful department of mathematics that we have at Cochin University of Science and Technology. So may his health improve, and let us all pray God that he will be able to physically attend the next endowment lecture next year, 2023. And I wish him a very long life. Of course, most of us are attached to his family members also, his wife, Dharmali Chechi, son Dineshan, and wife and grandchildren, and so on. I used to talk to him at least once in a week, every week. And I wish him long life and healthy life, and wish the program all success. And I invite Professor Thrivikraman to say a few words of his feelings about his experience in mathematics and Cochin University. Hello, sir. Sir.
Thank you for the remarks that you have made. I was a mathematics teacher for around 52 years, from the age 21 till 73. And the middle 26 years were at Cochin University. And during that period, I could guide the research work of many people, including Dr. Vijaykumar. I think the number will run to 34 or 35, something like that. But I don't claim the credit to any of these. All these because of the encouragement and blessings of 2 or 3 people. I have to mention their names. Professor Wasir Hassan Abdi, the founder professor of Cochin University Mathematics Department. Then before that, late Professor V. Karunagara, who was a professor at Maharaja's College. Professor P.I. Daniel, professor and head of the department of Maharathanish's College, and many and many others. So the credit is not to me, but to all these people, and I accept them on their behalf. Anyway, I'm thankful to the people who arranged this endowment lecture, and I hope it would be useful to all those who attend to it. Professor Murty would give you the necessary output. Anyway, the topic is brain networks and graph theory, which would be interesting to me also because I am interested in graph theory in particular. Thank you all.
Thank you, sir. Vyoma, sir, you may start.
Yes. I'm extremely happy to introduce the speaker, Professor Ramurthy, who hailed from Guntur, India, and he graduated with BSc from Carleton University and his PhD in 1980 from Massachusetts Institute of Technology. He was a faculty member of McGill University from 1982 to 96 and joined Queen's University, where he is a professor of philosophy, Indian philosophy also. His areas of interest include number theory, modular forms, and elliptic curves. And he has often collaborated with his younger brother, Kumar Murty, who is currently the director of the Fields Institute, Canada. Among the several accolades that Professor Murty has received include Coxeter James Prize of Canadian Mathematical Society, and he is a fellow of the Royal Society of Canada, and also elected to the Indian National Science Academy, and also as a fellow of the American Mathematical Society. He has several beautiful books. One which I would definitely mention is his first course in graph theory and combinatorics, along with my good old friend Sebastian Sioba, and also a book on Indian philosophy, and also along with Kumar Murty, the book on mathematical legacy of Srinivasa Ramanujan. If you Google, there are plenty of beautiful books by him on transcendental number theory and related topics in number theory. We have great pleasure that Professor Ramurthy readily agreed to give this second endowment lecture, jointly organized by the Department of Mathematics, Cochin University, and Rajagiri School of Engineering and Technology. So on behalf of all of us present in this forum, let me accord a warm welcome to Professor Ramurthy and request him to start his lecture. Professor Ram.
Thank you very much. So let me begin by sharing my screen. I think somebody needs to give me permission to share the screen. Okay. Can this be seen by everybody?
Yes, okay.
Did you want me to put it in full screen mode, or is that better?
This is fine.
Okay, so let me begin by thanking my distinguished colleagues and organizers of this conference, and wish Professor Thrivikraman and his family a long and healthy and inspired life. Looking at the expertise of Professor Thrivikraman, I see that we share several common interests, one of them being graph theory and the other being a commitment to mathematical education in the largest sense of the word. So I'm very happy and honored to be part of this endowment lecture. So the topic of this lecture is brain networks and graph theory. Oops, I think I have a problem here with my, is this all visible? Is it coming out to be pretty bad, or what's happened here? Are you getting some fractured
Yeah, initially, but now it is okay.
Yes, but I think if you don't mind, I will try to correct it. Can you give me a few minutes?
Yeah.
Okay, I'm unable to do that. So what I'll just continue as best as I can. Is this better? This is better, right? I think.
Yeah, it is better. Yeah.
Okay. So yes, you never know with this technology what the problems are. Okay. So let me begin. So the human brain and its mysteries. So the human brain seems to be the final frontier of science. Now, in Indian philosophy, brain, mind, and consciousness are three distinct entities, with the last two being the focus of philosophical inquiry. Now, much of Indian philosophy is devoted to the study of mind and consciousness, and much of scientific thought is invested in trying to study the brain. The Taittiriya Upanishad speaks about 5 layers of the human being: the physical body, the Annamaya Kosha, the nervous system, the Pranamaya Kosha, the mental body, the Manomaya Kosha, the wisdom body, Vijnanamaya Kosha, and finally pure awareness, Anandamaya Kosha. And the Subala Upanishad and many of the other Yoga Upanishads speak about 72,000 nerves in the human body and describe the main nerves and their function. So the topic of the brain network has been a focus of attention even as far back as the Upanishads. In the 21st century, neuroscience has made significant advances in describing the neural network of the brain, but the work has only just begun. And in this talk, graph theory is now the primary tool to describe various aspects of brain connectivity. And my goal in this talk is to give a general introduction to this interdisciplinary theme and also discuss recent joint work with my neuroscientist colleague, Professor A.N. Prasad. So I'll try to be as gentle as possible with respect to prerequisites in both graph theory and neuroscience. So we won't be assuming any deep knowledge of either graph theory or neuroscience. Let me begin by quoting Kant on the mystery of the mind. Kant, as many of you know, was the Enlightenment philosopher of the 19th century. In his critique of practical reason, Immanuel Kant wrote, "Two things fill me with awe and admiration: the starry heavens above and the moral law within." Very nice quotation. We've explored vast tracts of outer space with remarkable technological advances. But when it comes to exploring the inner space of the human mind, we've been quite deficient. As many of you know, with the Webb telescope and many other, the Hubble telescope, the Chandra telescope, and so on and so forth, we've been able to explore the farthest reaches of the universe, but we are sadly deficient when it comes to the nearest cosmos that exists within the human mind. Part of this reason is that we've not had the tools to do so. But with the advances in electrophysiological monitoring methods like EEG, we're slowly determining the neural architecture of the brain. Now we can use methods of graph theory to study brain networks, which is essentially the gateway to the mind. The microscopic structure of the human brain was first analyzed by the Spanish scientist Santiago Ramon y Cajal. And he's the first person to begin a serious clinical investigation into the structure of the human brain. And he's credited with the discovery of the neuron. A neuron is a nerve cell which communicates with other nerve cells through electrochemical impulses transmitted via connections called synapses or axonal dendrites. His neuronal theory is considered the foundation of neuroscience. In a lecture to the Royal Society of London in 1894, he said, "The ability of neurons to grow in an adult and their power to create new connections can explain learning." So you see, from this discovery, we see that the human being is a biological organism constructed, equipped with the ability to learn. This is considered to be the basis for the synaptic theory of memory. Excuse me, can you have people mute their microphone, please? Hello? Hello, can you, hello? Hello, can you have everyone mute their microphone, please? Okay, thank you. This is considered to be the basis for the synaptic theory of memory. Cajal was awarded the 1906 Nobel Prize in Medicine for this work. The emergent functions of the neural networks. So following Cajal, there was Rafael Lorente. He was Cajal's student. He advanced the theory that many of the brain functions are actually emergent functions of a network working in concert. So he advanced the theory of recurrent connectivity and showed that nerves transmit electrical impulses. The key word in this sentence is recurrence. And as many of you know, recurrence is a very important topic in mathematics, and the theory of Markov chains is a fundamental tool to study recurrence. His work was further developed by Donald Hebb, whose work has led to the basic mantra of neuroscience, that neurons that fire together wire together. And this gives a neurological basis for habit formation and human behavior. Hebb's 1949 book, The Organization of Behavior, is considered as a foundational book for the development of neuroscience. Some consider it on par with Darwin's Origin of the Species. Now, the connectivity matrix of the neural networks is easy to describe. These researchers have now established that brain functions are the outcome of neural assemblies that are interconnected. These interconnections can be visualized through the mathematical concept of a graph, whose vertices are either neurons or assemblies of neurons, and the edges are the interconnections between them. The adjacency matrix, with which we're all familiar, is also called the connectivity matrix in neuroscience. The edges are not undirected, but directed in the field of neuroscience, because synaptic connections are not necessarily bidirectional. So in addition, the edges may be weighted to measure the strength of the synapse. So the strength of the synaptic current might differ from neuron to neuron, and this also must be taken into account. We're thus led to represent these brain networks as a weighted directed graphs and can study them using methods of graph theory. Let me describe what are now called hubs of the brain network. From a clinical neuroscience perspective, it is important to identify regions of the brain network where there's more electrical activity, and these are called hubs. Several metrics have been introduced to determine hubs, ranging from the naive to the profound. The most naive, of course, is degree centrality, in which those nodes with the highest degree play the role of a hub. Another measure is the betweenness centrality, in which a hub is recognized as a node in which a high percentage of geodesic paths pass through that node. A geodesic path is the shortest path between 2 points. So we look at the geodesic paths that pass through a particular node. For the high percentage of such paths pass through a particular node, we may call that a betweenness centrality hub. Yet another measure is what is called Eigenvector Centrality, which is closely related to viewing the brain network as a Markup process and is akin to the Google PageRank algorithm. So that'll be the focus of this particular talk. So how to understand the brain network using graph theory? So we know that neurons communicate with other neurons and cells via chemical electrical interactions, and these communications can partially be measured through non-invasive methods such as EEG, fMRI, and so on and so forth. So an initial model can begin by using graph theory, with the nodes of the graph being either the neurons or neuron assemblies, and weighted directed edges indicating the line of communication along with the strength of the signal. This is what neuroscience is now attempting to do. And the Human Connectome Project, started only 20 years ago, seeks to map out all the neurons and their connections of the human brain. Now, how many neurons are there? Well, there are 100 billion neurons. So this is a mammoth project. And this work began only 20 years ago and still is in its infancy. Now, how far have we gotten in the study of the neural network of organisms? Well, so far, we only know the entire neural network of one organism, the microscopic roundworm called C. elegans. You can see it here, which is a total of about 300 neurons. And we'll return to this example later on in this talk. Let me begin by discussing the humble origins of graph theory for many of the students in the audience, as well as non-specialists. Graph theory first arose as a form of recreational mathematics, and many trace it to Euler's solution of the famous Königsberg bridge problem. So here's a picture of Euler. If you see that Euler with his right eye is kind of winking or something, it's because he had a defect from birth that made him look like that. One of his eyes was never functioning properly. So the Königsberg bridge problem considers 7 bridges. So you have this island here called A, and another island here, D. This is the mainland C, and this is the mainland B, and there are 7 bridges, A, B, C, D, E, F, and G. The problem was to walk across each bridge only once and cross all the bridges and return to the starting point. Euler showed that there's no solution using graph theory. So in some sense, it's the first application of graph theory. And he did this by first simplifying the problem. So here's the bridge connections here. And he represented this bridge by edges. Each bridge here is an edge. And these points A, C, D, B are the land masses. So what he noticed was if there was such a path, then it must enter the vertex and then leave by another edge, because you can't cross the same thing twice. So it's a necessary condition that somehow the degree has to be even. And then by using a very clever inductive argument, he showed it was also sufficient. So using basic induction, mathematical induction, and bit of basic graph theory, he showed that there is no solution to the problem. So it's a kind of a negative solution, but it's interesting that mathematics came to the rescue instead of people trying things by trial and error. So this set the stage for developing a more profound theory of graph theory. And graph is a collection of nodes, sometimes called vertices, and edges connecting some or all of them. And these edges can be weighted, and the edges can also have direction. So in the most general graph is a directed weighted graph. So here's a little example. Here's a little bunch of nodes, A, B, C, D, and E. And you have these edges, you have these directed edges, and you have weights. So the edge going from A to B has weight 4, from B to C, B to D has weight 3, and so on and so forth. And then this is the picture of a particular directed graph. And then to this directed graph, weighted graph, we can associate an adjacency or connectivity matrix as follows. So the rows and the columns parameterize the nodes, and then in the A, B coordinate, you would put 4 because that's the weight. If A and A are not connected, therefore it's 0. A and C are not connected. There's no directed edge going from A to C, so that's 0, and so on and so forth. So you encode this directed graph and the weights information into a matrix. And this is an amazing idea in itself, because the matrix is a mathematical object now with which you can perform group operations. And so maybe the theory of matrices can give us some knowledge about the graph. So the importance of graph theory, apart from its intrinsic beauty as a part of pure mathematics, graph theory has been useful in understanding complicated and interconnected processes. So they've been used to model communication networks. Here's an example illustrating Indian air routes. So if you have all the cities in India, they're connected by various air routes. And so this is a particular graph. It could be a directed graph. Here, the cities are the nodes, and they're connected by an edge if there's an air route between them. And you can weight the edges by, let's say, the cost of flying from point A to point B. And that would be the weight of the graph, weight of each edge. And a problem of graph theory is then how do you get from point A to point B with the minimum cost? You could also weight the graph with the time it takes to travel from point A to point B. And then the problem of graph theory would then be how to get from point A to point B with the minimum amount of time. And you may want to minimize both cost and time. And so again, these are general problems of graph theory, which have been solved. By the way, they're beautiful algorithms to solve these very fundamental problems. So this is the 20th century application of graph theory in the so-called real world. Now, the radius and diameter of a graph are important concepts. As the previous example shows, it's important to determine how fast can we go from point A to point B in any given graph. And to measure this, we need the concepts of radius and diameter of a graph. And one defines the given two nodes, x and y, we define the distance or the length as the shortest length of the shortest path between x to y. So it's got to be a directed back because we're looking at directed graphs. And the eccentricity E of x of a node is then defined as the maximum of the distance function, dxy. And the diameter and the radius of the graph are then the maximum minimum nodal eccentricities. So it turns out that the Bray network is a highly connected network, and the diameter and radius are both small. This is an amazing find, by the way. This phenomenon is often referred to as the small world phenomenon in neuroscience literature. So it's got this high connectivity. So without using too much hardware, the network seems to be able to go from point A to point B. So this is an amazing, it's shared by a class of graphs called expander graphs, and very much the Bray network shows the properties of expander graphs. The connectivity matrix, we've already indicated how to attach a matrix to a weighted graph. The most basic matrix to an unweighted, undirected graph is an adjacency matrix, and as I said, called the connectivity matrix. Because it is undirected, the matrix is symmetric. So most graph theory textbooks deal with undirected graphs. And so the adjacency matrices that appear are always symmetric, which simplifies the discussion from many points of view. Here are some examples. So here's some examples of graphs with 4 vertices leading to 3 adjacency matrices. So you can see that if you draw a line along the diagonal, the matrix is symmetric. So all these matrices are symmetric matrices. Now, modeling the Bray network via graphs, in the Bray network, the connections are not necessarily bidirectional. And so we really should be looking at directed graphs, also called digraphs in the literature. And our adjacency matrix A is not necessarily symmetric. Now, in our paper, my neuroscientist colleague Prasad and I introduced what we call the Markup Matrix P of a graph, whose XY entry is the reciprocal of the out degree of X. Could people mute their microphone, please? Hello? Can people mute their microphone? Thank you. Yeah. So P is row stochastic, which means that each row adds up to 1. All the entries of each row adds up to 1. And by the way, because each row adds up to 1, 1 is an eigenvalue of the matrix P. And it's easy to show that all the other eigenvalues of the matrix P are absolute value less than 1. This is going to be important in our discussion later on. The advantage of this perspective is that we can view the graph as describing a Markov process in probability theory. One can view the XY entry as the probability of going to a node or state Y, given that we're currently in node or state X. So now I'm taking a graph, a directed graph, and I'm now giving you adding another perspective of viewing this as modeling of Markov process. Spectral graph theory is focused on relating eigenvalues of the connectivity matrix to properties of the graph. And it seems that the Markov matrix is more suited to analyze the graph underlying the Bray network. So what is a Markov process? I've used that word already. Here's a simple example to illustrate a Markov process. In a certain town, it's observed that if it is sunny today, then there is 80% chance that it'll be sunny tomorrow and 20% chance of rain. So how do you get this number? Well, you would have to do statistical observations over a period of time, and then let's say a period of a year, and you notice this phenomenon, and then you record this. And if it is rainy today, there's a 60% chance of sunshine tomorrow and 40% chance of rain. So you make these empirical observations over a period of time. Having done that, we can then model this as a two-state Markup process, and we can represent it as a directed graph. So the two nodes are sunny and rainy. And if I'm sunny today, the probability of moving to sunny tomorrow is 0.8. So I indicate that as a directed edge coming back to the sunny with a weight of 0.8. If I'm sunny today, the probability that it'll be rainy tomorrow is 20%. So I indicate that as a directed edge going from sunny to rainy with the probability of 0.2. And if it's rainy today, the chance that it'll be rainy tomorrow is 40%. So I will indicate that as another directed edge with a weight of 0.4. If it's rainy today, the probability that it'll be sunny tomorrow is 60%. Therefore, I will indicate that as a directed edge going from with weight 0.60%, which is 0.6. So we can indicate this two-state Markov process with this directed graph. And having done so, we can now associate a matrix with it, as I indicated in the earlier slides. And here it is, the rows and columns are indicated by the two states, and the probability of moving from sunny to sunny is 0.8, from sunny to rainy is 0.2, and so on and so forth. So you have this nice matrix, which is now a mathematical object. And with P as a transition matrix, the situation 2 days from now is given by P squared. This is Markov's theorem. So once you model this process, what is the probability 2 days from now that it'll be sunny? What is the probability 2 days from now it'll be rainy? Can be read off by squaring the matrix. And in general, n days from now, it's the nth power of the matrix. It's an amazing, beautiful theorem. And then the next part of the theorem says that the power p to the n converges to a matrix limit. And then if you want to find what that limit is, you get that by solving the equation Vp equals V. And Vp equals V makes the problem into a linear algebra problem. So you're trying to find V. So V's are the unknowns, and everybody in the audience knows that the Vp equals V equation is a basic linear algebra problem. So in this particular example, if you solve that linear algebra problem, it turns out that V equals 3/4, 1/4. And what does that mean? It means that, in other words, it's sunny 3/4 of the time and rainy 1/4 of the time. This is a very interesting example. It's a very basic example, of course, but already illustrates to you the power of the Markov theory. So what is Markov's theorem? So let's look at the general case. He envisioned a process that can be in any given time in one of m possible states. In the previous example, the process was the weather, and the two states were sunny and rainy. But you could see that you could model many other things. For example, the mood swings of an individual in a similar way as happy and sad, with the transition probabilities encoding the probability of moving from one state to the other. This could be very useful in psychology. It's already also been used in epidemiology, where certain virus mutates into another variant, and you can model that as well. And of course, as we all know, COVID-19 now has about a dozen variants. So you could model the mutations of the COVID virus is a Markov process as well. Many processes in life are not two states, but maybe many states. In general, the case of m states, we have a transition probability matrix P, which is m by m. And Markov's theorem essentially states that P to the n now converges. I say essentially because there's small technical conditions, which I'm not going to discuss right now. States that P to the n converges to a limit, which can be determined by solving the equation Vp equals V. And for those of you who want to know what the limit is, the limit turns out to be J times P, where J is the matrix consisting of all ones. But V is needed, the vector V is needed. The jth component of the vector V encodes the probability of the process being in state J at time infinity. So amazing thing is, it doesn't matter where you started from, the limit vector can be determined. So this is a very profound discovery. Markov and the philosophy of Markov chains. So let's have a little bit historical interlude here. So here's Markov, and here is Markov with his wife, Maria, and apparently the desk on which he discovered the theory of Markov chains. So Markov began by studying recurrence. And as many of you know, recurrence is a common theme in mathematics, especially number theory and combinatorics. He started working out number theory under Chebyshev. His doctoral thesis developed the theory of continued fractions, in which recurrence occurs, by the way. Many of you know something about theory of continued fractions. And so his thesis was outstanding, and he was immediately appointed extraordinary professor at Petersburg University in Russia. His first paper developing the theory of recurrent chains was written in 1906, probably at that desk in that picture there. And it was only 20 years later, in 1926, that Bernstein saw its importance and gave the name Markov chains. I mean, Markov would never call his discovery Markov chains. He would just call them recurrent chains. But people did not pay attention to Markov's paper in 1906, and only later was it discovered that it was an important paper. Now, Markov had a very sad life, actually. For most of his childhood, he used crutches due to a severe inborn deformity in his knee. And at the age of 10, he had an operation on his knee, and afterwards he was able to walk only with a slight limp. And later in life, he developed an aneurysm in his leg, which led to multiple surgeries throughout the years. One of the operations on his leg was fatal, unfortunately, on July 20th, 1922. Markov died of sepsis, and he was only 66. Now, this picture is very interesting because you see Maria, his wife, he had met because in those days, women were not allowed to go to school. And I suppose something similar is happening now too, unfortunately, in the 21st century. But anyway, in those days, women could not go to school. Therefore, rich people would hire tutors to come and teach their female children. And Markov was one such instructor who taught an aristocratic family and met Maria there. And she learned mathematics from Markov, and they married, and she was his helpmate for much of his life. By all descriptions, it seems to be the classic story of Savitri and Satyavan of the Mahabharata, where the wife is a support and extends the life of the husband. So to give you an indication of mathematical genealogy, so here's how Markov is related to everybody else. Markov's advisor was Chebyshev, as most of you know, famous for Chebyshev's inequality, Chebyshev in number theory, Chebyshev in probability theory, and many, many other disciplines. Then a Markov student was Tamarkin, who, being a Jewish refugee, immigrated to the United States during the Second World War and ended up at Brown University. And then he taught D.H. Lamer, famous for Lamer's conjecture, Lamer and number theory, who taught my advisor, Harold Stark, and yours truly is next in line in that genealogy. So there is some mathematical genetic connection to Markov. So let's go back to this idea of a directed graph as a Markov process. The idea of viewing a directed graph as a Markov process is not new. The Google search algorithm is based on this idea. But the idea can be used to model many complicated processes, such as the pandemic and states being the mutations of the virus, which I already kind of briefly alluded to. And applying Markov's theorem allows us to learn how the virus mutates and gives us a probabilistic understanding of the future states of the virus. So by understanding where this thing is going, we can prepare ourselves and control the present situation. Any directed graph can be viewed as a Markov process in the following way. Each node of the graph is viewed as a state, and the transition probability, Pxy, is 1 over d plus of x, where d plus is the out degree of x. This gives rise to what we call the Markov matrix P of the graph. In this way, we now have two matrices associated to the underlying graph, the connectivity matrix and the Markup matrix. And the spectral theory of both these graphs gives us knowledge of the graph. Most often, in graph theory, when they talk about spectral graph theory, they're always talking about the spectrum of the adjacency or connectivity matrix. But now we propose that it's important to study the Markov matrix and the spectral theory of that. I'm going to give an illustration of how it can be used in this talk. So the brain network and the brain hubs. It's only in the last 20 years neuroscientists have found the language of graph theory convenient to model the neural network of the brain and are using it to study its architecture and functioning. It's becoming increasingly clear that the brain has to be studied as a dynamic process of neural between something like 100 billion neurons, which using our directed graph Markov model, we can call the states of the process. So that's too many neurons. And so we may try to cut that down. In this model, hubs are brain regions with a large number of connections or that are situated at the junction of an important fiber pathways crucial for efficient network connection. Such hubs are vulnerable to pathological insults and consequently develop structural alterations that enhance network excitability. And they seem to be implicated in many brain disorders, such as epilepsy. So my neuroscientist colleagues tell me that it's important to identify these hubs because they seem to be involved in many brain disorders. So maybe graph theory can offer a path towards understanding mental disorders. This is important to identify these hubs in the brain network, and this is the background of my collaboration with my neuroscientist colleague, Professor A.N. Prasad. So the discrete model of the brain network, in the simplest model, we associate two nodes I and J of a graph. If we say they're adjacent, if there's a synapse from I to J, and the discrete process then associates to G a matrix of transition probabilities, Pij, which is equal to the reciprocal of the out degree, as I mentioned in the previous slides. And if there's no synapse between I and J, the probability is set to 0. And it's convenient to call P the Markup matrix. We confine our attention to brain regions instead of all the neurons, as is often done in EEG. When you do an EEG, you take the brain, there are about 50 regions or so on the brain that they put electrodes on. And so we will use those as the nodes and try and see which ones are the hubs in that context. So a technical comment, as the number of neurons is finite, all neurons are recurrent and non-null, so that the fundamental theorem Markov chains applies. Now I'm not going to go into the technical definitions of this. This is the technical comment, and that's why it goes back to the Markov's theorem applies to recurrent non-null states. The theorem then is there's a stationary probability distribution V, which is determined by solving Vp equals V, and the coordinates of V encode the highest probabilities are then the candidates for the brain hubs. So modeling the EEG information into a brain network graph allows us to extract this matrix P, and then solving Vp equals V allows us to identify which coordinates of V have the highest probabilities, and those coordinates correspond to those regions which are the brain hubs. And from this perspective, we can get a new theorem on the radius and diameter of graph. Although the theorem applies to general directed graphs, let me just begin by stating the result for undirected graphs and indicate the modifications needed for the directed case. I'm going to do this because most of you are familiar with symmetric matrices, and you're familiar with diagonalizing symmetric matrices, and therefore it's much easier to understand that case first, and then I'll tell you how to modify the real symmetric case to the asymmetric case and use the appropriate theorem. So matrix is now row stochastic, P has eigenvalue 1, all other eigenvalues have absolute value less than 1, and if we let rho be the maximum absolute value of the non-trivial eigenvalues, then the theorem is if you have a connected undirected graph with matrix Markov matrix P, which is aperiodic, if you have V to be its unique stationary distribution of components Bi, the eccentricity of any node is bounded by log Bi over log rho, and the diameter of G is bounded by 2 times maximum of log Vi over log rho. So this is a bound on the diameter of the graph in terms of the spectrum of the Markov matrix. In 1989, I say this because in 1989, in the Journal of the American Math Society, Fan Chung derived bounds for regular graphs in terms of eigenvalues of the adjacency matrix. And that was a major breakthrough for communication networks. Ramanujan graphs are regular graphs and thus fit into Chung's theorem. But by all indications, the brain network is not a Ramanujan graph, nor is it a regular graph. And so the above theorem seems to be the more appropriate one to use in the context of neuroscience. Okay, I'm going to just flash this because I might be running out of time. Let G have M nodes. So you diagonalize the matrix. And the interesting thing about diagonalizing the matrix is if you take the nth power of this, you get this neat, very clean idea. And then when I try to understand what is the ijth coordinate of the nth power, I can write it as Cik lambda Q the mbkj. Using the fact that 1 is an eigenvalue, lambda 1 equals 1, and all the other non-trivial eigenvalues have absolute values strictly less than 1, I see that the Vj, the component, has this limit. And a few things are used. The first column of C has constant entries 1 over root n, because the columns of C are the orthonormal basis eigenvectors. So remember, since 1 is an eigenvalue with the eigenvector equaling 1, 1, 1, 1, 1, but you have to normalize it, so you have 1 over root n. So you get that as the first column of C, and then using that piece of information, you get this remarkable limit there. So this is basically Markov's theorem. I just gave you a proof in a nutshell. It is linear algebra at its best, linear algebra that we teach undergraduate students. So applying Cauchy-Schwarz to the thing, we can make this a little finer, and you get this inequality in terms of the non-trivial eigenvalues of the Markov matrix. And then finally, the theorem is proved. I'm not going to go into the details, as I said, because I'm running out of time. And one of the important things to modify it for the directed graph case has to do with use of Perron-Frobenius theorem. So here are Perron-Frobenius, who proved this theorem around 1908, which is the same time as Markov was doing his work. And I find always this fascinating. Professor Thrivikraman has an interest in history of mathematics, and so do I. I always find this fascinating, this so-called synchronicity of mathematical ideas. Somebody is doing something here, and somebody is doing something there, all doing at the same time. And at that time, they do not communicate with each other and do not know that the things are related. Only much later do we find out that they were doing it at the same time, and they are interconnected. So this is one profound example of such synchronicity. And I'm just going to flash this again. There's this Perron-Frobenius theorem. So we're not dealing with a symmetric matrix here. We're dealing with an arbitrary non-negative matrix. So this is an interesting phenomenon. Perron-Frobenius studied non-negative matrices and developed this diagonalization theorem, which I need. And there are not very many books that have this beautiful theorem. The first one that I could find was D.R. Cox's book, Theory of Stochastic Processes. And then it allows you to diagonalize a non-negative matrix. It doesn't have to be symmetric. You can diagonalize it by using a matrix H in such a way that this happens, and then you can control the eigenvalues. And you can use this theorem now to modify the theorem that I talked about earlier in the directed graph case. So this is the non-trivial piece of information that you need to inject into the study. So using this theorem, we can extend our theorem to the case of a digraph. And now let's go back and apply this to this roundworm that I talked about, Caenorhabditis elegans. As mentioned earlier, there's only one organism for which we have the entire neural network mapped out. And believe it or not, this worm has been the subject of considerable attention in the literature and the proceedings of Royal Society of Biological Sciences, dedicating an entire issue to it in 2018. And the connectivity matrix of this worm is available online from the Dynamic Connectome Lab. And the connection matrix has about 279 neurons linked by 6,393 chemical synapses, 890 electrical junctions, and 1,410 neuromuscular junctions. So even this tiny worm is a complicated neural network. And when you plot it, you end up getting this kind of a picture. And this picture I took from Olaf Sporn's book, Networks in the Brain, which is a beautiful book. Certainly a gentle introduction to how graph theory and neuroscience are connected. So our theory shows that there are only two hubs in this. So if you apply this theorem, the theorem that I obtained with Prasad, it shows that there are only two hubs in this network, PCBL and PCBR, corresponding to forward motion. So if you're looking at this worm, this is the front part of the worm, this is the back part of the worm. So forward motion, the worm moves in a forward direction, but there's another neuron that detects any harsh touch to the tail. So these are the hubs of the C. elegans worm. So my joke is that if this worm has an epileptic fit, we are able to figure out where it's happening. So we're far away from the human situation. Now, in real life, most likely in the neural model, it's not the discrete model that probably has to be applied. It has to be the continuous time Markov model. So we've used the discrete time Markov model to simplify matters, but the brain is a complicated network evolving in time. And many of you know that the neurons are not fixed. There's a certain plasticity of the brain. The more you use the brain, the better it gets. So this is why learning, teaching and learning keeps the brain alive, because the brain is an organism for learning. So, and it's evolving in time. So probably looking at it as a discrete time model is probably the wrong thing. We should look at it as a continuous time Markov model. Now, fortunately, the continuous time Markov theory has been studied as well. And now to understand that, the transition probabilities are replaced by functions of time. And then these functions can be measures of synaptic strengths. And the theory of continuous time Markov chains is equally elegant, and one can derive a stationary distribution for it as well. In a nutshell, one associates a new matrix Q called the matrix of transition probabilities. Using these transition probabilities Qij's, the stationary distribution of the matrix P of T is determined by solving VQ equals 0 this time. So this Q is the matrix of these quantities, which is a bunch of numbers again. And then you can use linear algebra to solve this, and that determines the stationary distribution of this continuous time phenomenon. There are various hypotheses regarding the shape of this P of T, and we plan to explore these in the future work. And one more interesting idea that emerged from our work is that motivates us to define what's called the zeta function of a finite network using the Markov matrix. And we propose that the zeta function should be exponential of summation p to the n over n. This is, again, a matrix. Exponential of a matrix is, again, a matrix. Zeta function is a matrix function and resembles zeta functions of number theory in many ways. For instance, the ideas of the proof that I gave on the previous slides can be used to show that it's a matrix of rational functions. So this leads to some intriguing questions. How are the singularities of the zeta function related to the function of the brain? Are the zeta functions of individuals different, or are they generically the same? These are kind of questions that are very interesting domain for future research. And one of the intriguing findings of recent work, 2000, Barbassi and Albert showed that many networks exhibit a power law in their distribution. They noticed that the probability of the random node has degree k is 1 over k to the s for some suitable value of s. And the brain network seems to exhibit such a law. This is in striking contrast to random graphs that seem to exhibit a Poisson distribution. So if you study random graphs, the degree distribution is given by Poisson law. Whereas in this case of these brain networks, it seems to be 1 over k to the s. Now, as the probabilities have to add up to 1, we humorously suggested in our paper that maybe the probability, the degree distribution is given by 1 over zeta s times k minus s, where zeta of s is the Riemann zeta function. And since I've been studying the Riemann zeta function all my life, I thought this was very interesting that it enters into the brain network in this fashion. So many intriguing questions that will be taken up in future work. So let me just summarize. We've presented new models to identify brain network hubs that may be of use in the treatment of epilepsy and other brain disorders. As various modalities of measurement are available, it should be possible to clinically test, or at least simulate, the validity of this hypothesis. The study of brain networks using graph theory suggests also retrospective graph theory from a neuroscience perspective, like I've talked about the radius and the diameter of the graph, using the spectral theory of P instead of the spectral theory of the adjacency matrix. So you kind of go back and do things, redo things. So as indicated in this talk, this leads to new theorems in even classical graph theory in terms of spectral theory of the Markov matrix. So we have discovered a new symbiosis between graph theory and neuroscience. Not only can graph theory lead to insights in neuroscience, but questions in neuroscience can lead to new theorems in graph theory. So the future of brain network research, it seems fitting to conclude this talk with a quote by Olaf Sporns that reflects the interdisciplinary nature of this research. Neither armchair theorizing nor formal mathematical analysis is sufficient to deal with the rich spatio-temporal structure of complex systems. Instead, computer simulations of such systems are necessary to form and test hypotheses and to gain mechanistic insight. Without the use of computer simulations, it would be impossible to explore complex physical processes such as the formation of planets, from spinning circumstellar disks of gas and dust, the impact of human activity on climate change, or the folding of proteins. So graph theory will be one of the many disciplines needed to understand the brain, not only the brain, but probably climate change, many, many other things. So we're entering a new era, but it will involve many disciplines coming together. So the brain is indeed the final frontier of science. All the disciplines seem to be converging into that direction. So thank you very much for your attention.
Thank you very much, Professor Ramurthy. So now the forum is open for discussion. If you have any questions, you can directly unmute and talk to him. Please.
May I have a question? Yeah,
Yes, please. Yeah, you can ask.
This power law of the brain network, does it suggest some fractal or chaotic structure of the network?
I couldn't quite get that. Could you please repeat it?
The power law of the brain network,
Yeah.
does it suggest some fractal or chaotic structure of the network?
Oh, okay. I wouldn't say chaotic structure. I would say perhaps maybe some sort of fractal structure. Yes, I think there's worlds. You know, one of the nice phrases that I've seen: networks within networks within networks. So these are. It's not just one network with 100 billion neurons that you analyze, but there's things within things within things, and I find that fascinating because in the Yoga Vasishta, the mind is described as world within world within world. So it's the same kind of idea. And I think that's a kind of a fractal description of what you're saying. Yeah, yes, I think the power law points to something like that. Yes, correct.
Thank you. Thank you.
Nice talk, Professor. Can you suggest some reference reading materials on this?
Yeah, I would recommend the one that I suggested, Olaf Sporns, Brain Networks, Networks of the Brain. At least that's the
Olaf Sporn.
Olaf Sporns, S-P-O-R-N-S.
Okay.
It's probably not a good idea to read too much. As an educator, I'm very cautious about telling people to read 100 things, but pick one, and this book is very friendly.
Yeah. Can you put it in chat box, the exact name?
I can put it in my chat box. I can also provide Professor Ambat Vijay Kumar with the slides of my talk so that everybody has them.
Fine. Yeah.
Hello. Hello. I'm Ganesh Kodu from Mathematics Department of Pune University. I have a question about, in the last slide you mentioned that, this formation of planets from, dust and, various things in the universe. There also these things can be applied. So is there any work in this direction?
I think there is, but I think many of these applications, at least my amateur take on it seems to be that mathematicians are not paying attention to some of these applications outside of mathematics in a very intense sort of way, and I think even the neuroscience applications that I've been noticing, what's been happening is the neuroscience people have a certain raw data and they go to the graph theory books. They're looking for the theorem to apply that to their context. And what my point in the talk that I gave just now is that there may not be the theorem that they need there, because we have been looking at things most of the time from an undirected graph perspective. And these are directed graphs. And so you kind of have to redo a few things. And it requires you have to go to the, have to be a serious mathematician and understand these things. So let's say understanding the formation of stars or the mutations of viruses, epidemiology, and so on and so forth, the interdisciplinary nature seems to be mostly of a nature where a person kind of goes into the library, consults the books, and tries to look for the theorem that they need. Whereas I'm just trying to say that the dialogue has to be more intense, and it has to be a symbiosis of discoveries from both sides.
Okay.
Yeah.
Thanks a lot.
Can I ask a question? Can I ask a question?
Yes, please.
Yeah. So, Professor, it was very good to hear you. And one comment what I would like to make is that we have already learned about neural nets, which is somewhat like an application of brain science on computer science. And now today we heard about how the graph theory is being applied to understand the brain itself. So my question is that how long is this field? How long is this research going on? From which year it has started, and how much matured it is in this particular application?
Yeah, that's a very good question. If you, it's only 20 years old, believe it or not. It's surprising.
20 years.
20 years old. And Olaf Sporn's book actually tells we're really at the beginning of this thing. The reason for part of it has to do with only after the internet has emerged were we starting to understand network mathematics, where it's not individual neurons that explain certain phenomenon, but networks of neurons. Yes, that's so. This is what they call emergent functions. So systems biology, for example, also discusses networks operating in concert. So the human being, the way I understand my take on Indian philosophy versus ancient science, is that many of these processes, network processes of the human body, the human being, the human mind, have been discussed as gods in the Indian system. For example, the respiratory system is a whole network working in concert. And if I understand the Vedic literature correctly, Vayu or prana, the pranic system, is referring to the respiratory system. Agni, again, Agni, the digestive fire is Vaishwanara. So the digestive system is, again, it's not just the stomach alone, but it's the whole thing working in concert. So one of the things that came up in the later part of the 20th century is that we have to understand systems working in concert. And so that collective system working in concert gives rise to an emergent function. The function cannot be localized to a particular node or a particular neuron or particular cell. It has to be looked at in the totality. And that network mathematics, network theory is a 20th century, later part of the 20th century, and largely motivated by problems of large scale things like internet and so on and so forth. So that it makes sense from that perspective. And it was only recently that people got the idea to apply graph theory to neuroscience and found that the language will enable them to understand things much better.
Thank you.
Professor Ram, but can I ask a small question?
Yes, please.
Professor Ram, this is Sophie here. We had met way back in Mohali, if you remember.
Oh, yes. Okay. Yes. Hello.
Right. So you had briefly referred to synchronicity of events or ideas in mathematics. But the fact remains that this simultaneity or this synchronicity happens across disciplines, not only in mathematics, physics, architecture, music,
right,
and many other endeavors. Can you make sense of this? I mean, how does one explain this synchronicity of ideas, events, phenomena?
You know, the Sankhya philosophy says that there's a universal mind, of which we're all part of that.
I see.
This is not my idea. It's Sankhya. Kapila is a founder of Sankhya philosophy. So you know, that's what Indian philosophy says, that we are all interconnected at a very deep level.
I see.
The mind is not an exception.
It's a beautiful book by name Linked, connecting various phenomena, as Professor Ramurthy mentioned.
Can you name the name of the book and the author?
Author, I don't remember. Name of the book is Linked, Linked.
Okay, I see. Is it an old one?
No. Everything could be less than 20 years.
I see. All right. Great.
Okay, I have a couple of questions. Yeah, Ashwani Kumar, please.
Hello, sir. Hello. Yes, sir. I'm a PhD student from IIT Indore. So I'm doing PhD in machine learning in mathematics department here. So I read, I don't know, this question is different from this presentation. I read this, the meeting of Sri Ramakrishna and Swami Vivekananda. So there is a note of Amra Murthy. So can I ask something about it from sir?
Sure.
The meeting of Sri Ramakrishna and Swami Vivekananda. So sir, can you please say something about this note? I think you have written this.
I forgot what I wrote. Can you tell? Do you have a specific question?
No, sir. Actually, I just see this PDF. So my question is, I mean, how this PDF is connected with this neural network or something else, or Indian philosophy?
Okay, yeah. So this is a good question that you've asked. You see, my take on things is now it goes back to Professor Sophie's question earlier with the universal mind. So you see, there the grand drama of life is incomprehensible by a single individual, and it seems to me that this collectivity, you know, of human thought and human knowledge is very important. I mean, how did we get this far? We have all gotten together, tried to share knowledge, share discoveries, and this is how we have been growing. As I mentioned in my talk, one of the most profound discoveries of neuroscience is that the human organism has been built to learn. The fundamental property of the neuron seems to be its ability to learn. You know, I don't know if you, many of the, you know, in preparation for this research that I've been doing with my colleague, I've also been attending various lectures in neuroscience, and remarkable experiments are showing that, for example, they took rats' brains and they blocked the visual cortex. They would send the visual signal through the eyes, but they would block the visual cortex of the rat so that it would be deflected to the audio cortex. And the neurons in the audio cortex started to gain the ability to see. So this is there's this adaptability, there's this plasticity, there is this neuronal learning capacity. So if I have to say, who am I? The Ramana Maharshi question, who am I? I am an organism that has been structured to learn. That's the reason for living is learning. So somehow, and that seems to be the remarkable thing. And so when I look at that and I see, yes, gigantic events, the kind of events that you described, the meeting of Ramakrishna and Vivekananda and the dialogue that ensues, the knowledge that ensues, gives us an opportunity to learn something from that. So this is how I see the human experience, the daily life. We are learning constantly, some at a very slow rate, some at a very fast rate, but the opportunity to use the day to learn seems to be the reason for living, as it were, even from a neuroscience perspective. So I hope that kind of, we can learn from many things from the great spiritual personalities that you alluded to, but we can learn from the sweeper as well. We can learn from everyday interactions as well.
Thank you, sir. Thank you very much.
Welcome.
Okay, I have some questions. You are approaching the theory through the Markov Matrix. And that too, the entry is reciprocal of the out degree. Is there any reason for that choice of reciprocals?
No, it's just the simplest version. So as I mentioned, the real thing should be a continuous time Markov model where it should be a function of time. And so as my neuroscience colleagues tell me, the synaptic strength functions have not been completely figured out. So that there should be some numbers. So just for the sake of simplicity, I use, so the Google does the same thing. Google, you put a search word in, it finds all the URLs with the search word, makes a graph where A goes to B if A links to B. And then the matrix is 1 over the out degree, and then runs the Markov theorem, and then spits out the entries in the order as predicted by the stability distribution, stationary distribution.
So this matrix is stochastic, aperiodic, and irreducible, so that you can apply the Perron-Frobenius theorem also.
Exactly, it is irreducible.
I see. And another interesting thing which I found that you could identify the hubs, isn't it?
Yes.
You know that there is a standard algorithm called Hits algorithm.
Yeah.
And identifying hubs in any such power law distribution or real world networks is not easy.
Mm.
And maybe that your worm has only some 300 neurons that you could calculate the hubs, isn't it?
Hubs, yeah, exactly.
So there are certain other living organisms where the number of neurons is very much less than, of course, that of human brain. So, and you said that it is the only result available in 2018 regarding the number of hubs of this worm.
Exactly.
That's an interesting observation.
That's right. And the other thing is that we have, there are other, I think some monkeys have been mapped and some mice also have been mapped. Not completely, but more or less. But these are huge matrices again. And so we're working with another colleague who knows this computer, who knows this stuff better than I do. And trying to see what this algorithm, our approach will give and how it can identify the hubs in the monkey and the mice.
Oh,
yeah.
It's a very exciting where you discuss several notions like protein-protein interaction networks, brain networks, World Wide Web, and everything.
Yes.
And somebody asked about a book. There is a book by, I don't remember the author, but the title is Fractals, Chaos, and Power Laws. That's a very good book which I used to refer on connecting fractal theory and power law distributions.
So can you please write the name in the chat box?
Fractals, Chaos, and Power Laws.
Yeah, and I think somebody already alluded to the fact that there's a fractal nature of the brain network.
Yes. I hope that there are no other questions. So the talk was really exciting as expected it to be. And I now hand over to Vinod.
So I thank Professor Ramurthy for stimulating our brain. Thank you. Thank you, Professor Ramurthy, for excellent and enlightening lecture. Thank you. Thank you very much. I thank all the participants, PT sir, Vijayomar sir, Dr. Shashigopalan, and I think Professor M.N. Narayanan Nambudiri has joined for the event. He is formerly with Cochin University and is still continuing there as emeritus professor. I thank all the participants. Thank you all.
Thank you. Thank you, Ram, for being here. It's so early morning. It's around 7 o'clock now or more than that?
It's 9:15 in the morning.
Oh, 9:15 is okay. Okay, thank you.
It's good to see all of you. Thank you again.
Thank you.
Thank you. Bye.
Thank you very much, sir.